Hello everyone. Today I'll be presenting my IoT internship project, a smart home monitoring system. This project demonstrates how Internet of Things technology can be used to create intelligent home automation and security solutions. Throughout this presentation, I'll explain system architecture, demonstrate the working prototype, and discuss the learning outcomes from this internship. Our agenda today includes introduction to IoT concepts, project objectives, system architecture, hardware and software implementation, demonstration, results and analysis, real-world application, future enhancements, and conclusion. Introduction to IoT. The Internet of Things refers to the network of physical devices embedded with sensors, software, and connectivity that enables them to collect and exchange data. IoT is revolutionizing how we interact with our environment. In homes, IoT enables smart automation, energy efficiency, and enhanced security. This project applies these IoT principles to create a practical smart home monitoring solution. Traditional home face several challenges: lack of real-time environmental monitoring, inefficient energy use, delayed security alerts, and no remote access to home status. These problems result in high energy bills, security risks, and inconvenience. Our IoT solution addresses these issues by providing continuous monitoring, instant alerts, and remote accessibility through cloud integration. This is our problem statement basically. Now we have the project objectives. The main objectives of this project are: first, to create a real-time monitoring system for temperature and humidity. Second, to implement motion-based security with instant alerts. Third, to integrate cloud storage for data analysis. Fourth, to provide remote access through web dashboard. And finally, to demonstrate practical IoT implementation using affordable components. Let me explain the system architecture. At the heart of the system is the ESP8266 Node MCU microcontroller, which has a built-in Wi-Fi capability. The DHT11 sensor measures the temperature and humidity. The PIR sensor detects motion for security purposes. Locally, we have an LCD display, LED indicators, and buzzer for alerts. The system connects to Wi-Fi and sends data to the ThingSpeak cloud platform. Users can access the dashboard from any device with internet connectivity. This architecture ensures data flow efficiently from sensors through the controller to the cloud and finally to the user interface. Hardware and software implementation. Under that, let's look at the hardware components. The ESP8266 Node MCU is a low-cost Wi-Fi microchip with a full TCP/IP stack capability. The DHT11 sensor measures temperature from 0 to 50 degrees Celsius and humidity from 20 to 90%. The PIR motion sensor detects the infrared radiation changes caused by moving objects. We also use an LED for status indication, a buzzer for audio alerts, and standard components like a breadboard and jumper wires. Here's the complete circuit diagram. The DHT11 sensor connects to the pin D4 with the power from 3.3 volt. The PIR sensor connects to D5. The LED with the current limiting resistor connects to D6. The buzzer connects to D7. If using an LCD display, it connects via I2C to pins D1 and D2. All components share common ground. The ESP8266 is powered through the USB port, which also allows programming. This design is simple yet robust, making it easy to assemble and troubleshoot. The software architecture follows a modular design. On startup, the system initializes GPIO pins, connects to Wi-Fi, and starts sensor readings. The main loop continuously reads sensor data every 2 seconds, checks for motion detection, updates the local display every second, and uploads to ThingSpeak every 30 seconds. We implement error handling for sensor failures and automatic Wi-Fi reconnection. This code is written in Arduino C++ and uses standard libraries for ESP8266 and sensors. Let me highlight key code functions. The connect to Wi-Fi function establishes network connection with retry logic. The read sensors function gets data from DHT11 with validation checks. The check motion sensor function monitors PIR status and triggers alert. The upload to ThingSpeak function sends data using HTTP GET requests with the proper URL encoding. Each function includes error handling to ensure system reliability. The code is well commented and follows best practices for embedded systems programming. ThingSpeak integration. The ThingSpeak is an IoT platform that provides data collection, visualization, and analysis. We created a channel with three fields: temperature, humidity, and motion status. Data is sent via HTTP API every 30 seconds. ThingSpeak generates real-time graphs automatically. We can set up alerts for specific conditions like temperature exceeding thresholds, etc. The platform offers MATLAB integration for advanced analytics. This cloud integration makes our local system accessible globally. Next, we have the demonstration. Under that, we have the system startup. The first visual shows the crucial system startup. The serial monitor confirms that the auto reconnect logic successfully established a Wi-Fi connection and assigned an IP address. This screenshot validates the core connectivity function, ensuring the system is stable and ready to transmit the data. Next, we have the normal operation. This slide illustrates normal operation. The system is continuously reading and logging stable temperature and humidity data. The ThingSpeak graph shown here confirms the successful continuous stable data logging to cloud platform every 30 seconds. Next is the motion detection. This visual captures the motion detection alert. When the PIR was triggered, the serial monitor instantly logged motion detected. The system simultaneously activated the local LED and the buzzer alerts, and the real-time status of one was immediately sent to the cloud, proving high responsiveness for security. Finally, we analyze the ThingSpeak dashboard. This historical data confirms stable environmental trends with a clear, distinct spike in the motion status field. This data validates that all critical events are successfully logged and stored in the cloud, and the platform allows us to export this CSV data for future analysis. Results and analysis. We conducted extensive testing over 1 week. Temperature readings were verified against a commercial thermometer with accuracy within plus or minus 1 degree Celsius. Humidity measurements matched reference devices within plus or minus 3%. Motion detection had a 98% accuracy with 2% false positives from the environmental factors. Wi-Fi connectivity remained stable for 48-hour continuous operation. Data upload success rate was 99.7% with only three failed transmissions out of 1,000. These results demonstrate system reliability. Challenges and solution. During development, we faced several challenges. Initial Wi-Fi connection was unstable. We solved this by implementing connection retry logic with exponential backoff. DHT11 occasionally returned invalid readings. We added data validation and kept previous valid values. ThingSpeak has a 15-second minimum interval. We adjusted our code to upload every 30 seconds. PIR sensor had a false triggers. We adjusted the sensitivity and added a warm-up period. These problem solving experience enhanced by my debugging skills. Learning outcome. This internship provided invaluable learning experiences. I gained practical skills in embedded systems, programming with Arduino framework. I learned ESP8266 Wi-Fi integration and HTTP communication protocols. I understood sensor interfacing and signal processing. I gained experience with cloud IoT platform and data visualization. I developed debugging skills for hardware software integration. I learned about the system design from requirement analysis to implementation and testing. These skills are directly applicable to professional IoT development roles. Real world application. This project has numerous real-world applications. In residential settings, it provides home security and comfort monitoring. In agriculture, a similar system monitors greenhouse conditions. In healthcare, it can track patient room environments. In industries, it enables equipment and facility monitoring. In smart city scaled version, monitor public spaces. The architecture is flexible enough to add more sensors like gas detectors, light sensors, or cameras. This demonstrates how IoT creates value across multiple domains. Future enhancements. Several enhancements can make the system more powerful. We could add email and SMS notification using IFTTT. We could create a mobile app for better user experience. We could implement machine learning to detect unusual patterns. We could add more sensors like gas, smoke, or water leak detectors. We could integrate with voice assistants like Alexa or Google Home. We could implement a local data logging with SD card for offline operation. We could add a remote control capabilities to turn on off appliances. These enhancements would make the system market ready. Conclusion. We successfully developed a fully functional IoT smart home monitoring system. We achieved all project objectives, real-time monitoring, motion detection, cloud integration, and remote access. The system demonstrates practical IoT implementation using affordable components. The skills gained during my this internship are valuable for my career in IoT and embedded systems. This project showcases how technology can make homes smarter, safer, and more efficient. Thank you for watching.